Sorry.
Good afternoon, one and all present here. It is with immense pleasure that I welcome you all to the International Technical Colloquium on exploring computational intelligence in deep learning, emerging trends and real-time applications, organized by the Department of Computer Science and Engineering at Kamaraj College of Engineering and Technology, Virudhunagar. As we embark on this intellectual journey over the next 5 days, let us seek God's guidance and blessings to inspire us with wisdom, clarity, and purpose as we delve into the fascinating world of deep learning and computational intelligence. This colloquium brings together deep learning experts, researchers, and thought leaders to share their invaluable insights and discoveries in the field of deep learning. Together, we aim to explore emerging trends, understand real-world applications, and inspire innovation that will lead the next wave of breakthroughs in this field. To officially inaugurate this event, it is my privilege to invite Dr. A. Meenakshi, Head of the Department of Computer Science and Engineering at Kamaraj, to deliver the welcome address. Ma'am, please.
Thank you, Mr. John. Good afternoon and a warm welcome to all the distinguished guests, esteemed speakers, and participants from around the globe. It gives me immense pleasure to welcome you to the 5-day International Technical Colloquium on exploring computational intelligence in deep learning, emerging trends and real-time applications. This online event brings together leading minds from academia, research and industry to explore the vast potential and advancements in the realm of deep learning and computational intelligence. We are in the middle of a technology and a technological revolution where artificial intelligence and machine learning are reshaping the way we solve complex real-world problems. Deep learning, as one of the most powerful subsets of AI, has demonstrated incredible success across various fields like healthcare, finance, and autonomous systems to natural language processing, computer vision, and beyond. The demand for computational intelligence in making sense of vast amount of data and enabling real-time applications has never been more critical. Over the course of next 5 days, we will delve into emerging trends through keynote speeches, technical sessions, panel discussions, and hands-on workshops led by the experts of research and development efforts. And my special thanks to the coordinators, Ms. Adilakshmi ma'am, Ms. Janani ma'am, and Ms. Leela Rani ma'am for making this happen. And also I am very thankful to each participant for joining us in this important event. Once again, a warm welcome to you all. Let's make this colloquium a platform for meaningful exchanges and a springboard for innovation. I wish you all a fruitful and engaging 5 days again. Thank you all.
Thank you, ma'am, for your warm and insightful words. Your leadership and vision have always been a source of inspiration, and your thoughts today have set the perfect tone for this colloquium. We are truly grateful for your unwavering support in making this event a reality. Thank you, ma'am. Now it's time to introduce the resource person of the first session. It's my pleasure to introduce the esteemed resource person for our first session, Dr. J. Jessu Vedanayak, Senior Assistant Professor at the Anna University Regional Campus, Tirunelveli. Dr. Jessu Vedanayahi has made significant contributions to the academic and research community, focusing on cutting-edge technologies that are reshaping the future of AI. With a deep understanding of generative models, Dr. Jessu Vedanayahi's insights will provide us with a comprehensive perspective on how these models work and their potential in real-world applications. We are truly honored to have her with us today to share her expertise in the crucial area of deep learning. Without further delay, let us warmly welcome Dr. J. Jessu Vedanayahi to lead the session. Over to you, ma'am.
Thank you, sir. Thank you for the introduction. And I thank the organizers for giving me this opportunity. And good afternoon to all the participants. Give me a moment. I'll share my presentation. Hope you are able to see my screen.
Yes, ma'am.
Yes, ma'am.
Yes. So once again I welcome you all, the participants who have shown interest to register for this 5-day online international technical colloquium on exploring computational intelligence in deep learning, emerging trends and real-time applications. Um, and once again, I congratulate the department. I congratulate the head of the department, the other coordinators for having planned for such an activity, for such an forum for discussions and new learning. And originally, yeah, my session was planned as a second session, which starts from 3 to 4. Uh, but due to some reasons, I'm just holding the first session for now. So that is on generative models. So here we are going to generative models. So though we are talking about artificial intelligence since 1950s, so this word AI is coined by John McCarthy somewhere in 1956. It's way back, almost so many decades back. But still, we come again with the topic of artificial intelligence. We are just uh, saying that our future will be artificial intelligence. But all these methodologies, their roots starts way back in 1950s and all. And today we are saying that artificial intelligence is not going to be our future. Even today, the present situation, we have started to experience a lot of applications where really we see the potential of artificial intelligence. That is because of one particular model coming in our artificial intelligence, that is generative models. So earlier, we were a decade back or even some years back, we were always into prediction. So how we use data to make predictions, but we are trying to make creation now. So this generative models, as the name suggests, they are going to generate or they are going to create. So this is my overview of my presentation. So we'll have an introduction and briefly I will take you through the types of AI, and then we will see what is generative AI, and then we'll see a brief history which will talk about important milestones of generative models, and we'll see the applications, and then we'll talk about some of the generative models which are very prominently known today, and then we'll see some of the darker side also, and we will conclude. So introduction. So we are in a very broad discipline called as artificial intelligence. Even we can think AI as a science discipline, like what physics is there. So AI is something like that. And a subsystem is machine learning, which we have been talking even a decade back or even several decades back. We have started to think about something called machine learning. And in recent years, we are talking about something called deep learning, which is the focus of this particular technical colloquium. And under deep learning, there is a particular subsystem or a subset, and that is what is generative models. So deep learning session will be handled by the other resource person in the next session. So where you'll be getting the foundations of this. But even generative models can be taught as a independent module. So I'm going to deal with this. So types of AI. So where we are today and where we are going to go with respect to types of AI. So here, yes. AI, it is broadly classified into two different categories. So under the category one, you're having three types, which we have seen conventionally in all our artificial intelligence textbooks. That is narrow AI or weak AI, strong AI, and super AI. So narrow AI, weak AI is what we were doing with the help of machine learning methods. That is the prediction mechanisms. We develop models which solve a particular problem or which are for a particular task. Example, they'll be predicting diseases or they will be predicting the climate, the natural disasters. So it is meant for a specific task and it cannot extend its knowledge to other functionalities. So when this is restricted, we call it as narrow AI or weak AI. And strong AI or general AI, it is otherwise called as general AI. So this is a type of AI where it is going to excel a little bit like humans. It is going to perform in the level of a human. So somewhere we have reached this milestone, strong AI today, in the sense that we are able to have chat GPT and other where the question answering is possible. We are able to question this model and the model is giving you right answers, different answers, which are probably very useful for us and for our students also. And we have somewhere reached this strong AI. And super AI is something which is going to excel or supersede the power of a human being. So, which is going to even outperform the capability of humans. So, we are not here yet. And when we reach it, maybe, I don't know what wonder will be there in the world at that time. And the second category is divided into four subtypes: reactive machines, limited memory, theory of mind, and self awareness. Reactive machines is just reacting to a stimuli, or when you give an input, it will be able to generate some output according to whatever is the conditions or whatever the programming what we have done. So this you call it as reactive machines. So like what humans react to situations, they act to stimuli. When you ask some question, they'll be answering it. But here the important problem of this lower level of AI is they don't have a memory. They don't support memory. So even in deep learning, you would have heard about a term called LSTM, long short-term memory. Even before this particular concept is came into existence, the models what we were using, CNNs or RNNs, they had this lack on remembrance or memory. So all those machines or all those models what we have developed before this point of LSTM is all reactive machines and limited memory. So here LSTM or other kind of stuff where you're able to store something and process it, remember something and act to the situation, we call that type of AI as limited memory AI. So we have reached this. Now with the help of ChatGPT and other Copilot and other type of GPT models, we have proved that computer could have a memory, it could remember, it could have a knowledge base, and it could answer the questions from the knowledge base. And theory of mind is somewhere, no, we are not there yet. It is a concept where you could understand the emotions of other human beings. When you have so much of research coming up in brain control interface, that is a study called BCI, we will be able to achieve this theory of mind. And something is self awareness. So we have so much of robots here, even citizens. Sophia is a citizen, actually, it's a robot. And if these robots come up with self awareness, that is, they are able to understand their difficulties, their emotions, their feelings, now we'll reach to a segment called self awareness. So we are nowhere at self awareness or super AI, but soon we are expecting to be there. Like what in 1950s, AI was funded, but then the funding for AI is stopped. Actually, it is stopped somewhere in 1980s. No funding was done for AI, and all the AI projects or research were dropped because the hardware available at that time, they didn't have the power to uh, support these models, these machine learning models. And because of this GPUs, graphical processing unit, and the huge amount of memory what is available in the last decade, we are able to come up with deep learning, and we are also talking about generative models. So here there is another way of classifying the AI models. One is the discriminative models, the other is the generative models. In the discriminative models, so this is what myself have done in research, or many of your um, scholars or you have done research on. That is, you try to make a prediction, you try to make categories try to predict the category. So here in this diagram, you could see that this line here is trying to make a boundary or a separation between two categories, one with all this blue features and the other with all this red features. But generative model, if you could see here, they are not trying to predict it, but they are trying to understand the meaning of all these red points and the meaning of all these blue points. And once they have understood the base, they will be able to create new points in this particular domain or in this particular category. So that is what is the power of generative AI. Okay. So this is a distinction between discriminative and generative models. So till now, whenever you have had data, you have trained it and you have used it to predict a class label, that comes under discriminative models. You might have used machine learning or you might have used deep learning. That's not a matter. You might have used even one of my scholar have used CNN to diabetes prediction, or another scholar has used CNN for Parkinson prediction. So you are just predicting a disease with the help of some training data. You're trying to classify whether the patient is having a disease, yes or no. If you're doing this, you call this type of learning as supervised learning, and this comes under the discriminative model category. Okay, so examples is like classifying the diseases, the severity of diseases, predicting the whether all whatever we have done till today help of you and I, if you have done some research on deep learning or machine learning, we are always into something called supervised learning or sometimes even unsupervised learning. Our ultimate aim was to predict something, okay, or classify something or group something. But generative model, it is trying to create, it is trying to create new points. It is trying to create new samples, create new observations by understanding the underlying data structure, understanding the nature of the samples. You are trying to infer what is the quality of the data, what is the feature of the data, what is the characters of the data, and hereafter I'll be able to generate more pixel. Okay, say for example, why if I say show a cat to a discriminative model, it will take all the features and it will try to understand that whenever these feature is there, I have to categorize this as cat. These features or cat. But when I show, of course, these features, but when I show an image to a generative model, it tries to understand not one cat picture, but I have to give several cat picture for it, and it will get trained on why and how it looks like a cat. And hereafter, if I'm asking the system not to predict whether a particular image is a cat, but I'm asking the system to generate a cat image. So that's the difference. Okay, so here it is specifically used to create new images of animals, birds, or even something which is not existing. So the first time when I attended a course on generative model, I started creating pictures of my own creativity. Yeah, a car which will have wings, a car which could fly, and so much. No, I was exploring so many things. An astronaut who is riding a car, a horse, something. This generative models will come up with pictures to enhance your creativity. Okay, and you're able to create text based on prompt like what you do in ChatGPT, and it's also able to do text summarization or text translation. Now coming to what is generative AI or generative model. So normally it is called even as Gen AI. It is basically you are having in learning, you are having two types, or sorry, actually exactly three types. One is, one second, I'll just take you through that and come back. Supervised learning. The other is unsupervised learning. So these two you might be familiar with. You take an input that is a training data which is labeled and you generate a model. Maybe it is a linear regression or logistic regression or artificial neural network. You train it, you generate a model, and hereafter you have a test data and you try to predict the label. Okay, and whenever that the predicted output is wrong, it will again give the input and the training will be happening. Okay, so this is a supervised learning model. In the case of unsupervised learning, you don't have a training set. That is, you don't have the data which is labeled. You are having only the data, but there is no category. There is no classification. There is no diseases, what is already existing. I have only the symptoms, or I have only the features. but I don't know what is the category to which it belongs to. The data is unlabeled. It is inherently unlabeled, or purposely I have removed the labeling. Now I create a model. So normally people who have come across machine learning already, you might have heard classification and clustering. Clustering comes under unsupervised learning and classification comes under supervised learning. Okay. So you group it and now you are trying to generate a label for it. And so this you call it as a supervised learning. You are generating a category based on the similarity existing among the features. You categorize that. Suppose I have the features of different animals. Okay, I have changed the image into feature, and these images are from different type of animals: cat, dogs, lion, tiger, and all. Now I don't have the category there, but based on the similarity of the data, I just put all these samples into one group, because all these look like a picture of a lion. All these look like picture of a cat. So if I generate a label and group them, I call it as unsupervised learning. Normally this is done in information retrieval, that is especially in World Wide Web. The documents are clustered, and here you call the learning as unsupervised learning. And in between those two, you are having something called semi-supervised learning. Okay, you're having something called semi-supervised learning. So semi-supervised learning also comes under generative models, or I can say generative models are either unsupervised or semi-supervised. When I say semi-supervised, I'm not having enough data. Okay, I'm having some samples which are labeled, and there are other samples which are not labeled, unlabeled. So it's a mixture of all. Uh, Say, for example, in some situations, there will be scarcity of data. Um, Sometime I attended a postdoc position in a foreign university. So there they were doing some drug analysis, okay, based on genomic study. In these type of domains, actually the data is very scarce. So they were doing something called transfer learning or zero shot learning or one shot learning. In these cases, they have samples, only very few samples, and all the remaining they don't have samples at all. In these cases, you can come up with something called unsupervised or semi-supervised learning mechanisms, where you have a trained model on some other domain where you have the data, and you apply this trained model to a different domain. Okay, so these are also possible with the help of generative models. And unsupervised and semi-supervised machine learning algorithms. So the basis is, the definition is, if you are going to create a new content with the help of existing content like text, audio, video, images, or even programming language codes. So if you are having a training set like this, and if you are training the model with the help of these data, the model will be able to generate new content. And this new content will look like original. Okay, the new content will look like real. Generative models, how they are doing it is, they are all neural networks actually. So these things, if you are doing deep learning and then coming to generative AI, it will be better, because in machine learning, you would have learned about some network called ANN. And this neural network is a complete basis for the domain called as deep learning. All the models what we have the basis on neural network. And again, generative models also have their basis on neural network. So all these models are using, because these models are mimicking the human brain. Human brain is nothing but a collection of neurons, connected neurons. So it is a neural network. So artificially, we are trying to mimic our brain, and that's how these models are able to outperform, or at least perform like human beings today. Okay. So generative AI models, they use neural networks to identify the patterns or the structures of the data. And once you understand, like what humans do, when we see cat, we differentiate the cat and dog, because a dog has different tail, ear looking, and the body texture, body color, and all. How humans differentiate a dog and a cat, the same way this neural networks is going to understand the data, and they are going to store the features of this particular category. And in the future, you ask them to generate a picture of a dog, they'll be able to generate a picture of a dog. Or if you ask them to generate a picture of a cat, they'll be able to generate a picture of a cat. And for this, all this generative models are guided by something called user prompt. That is, we have to ask the right question to get the right answer. And now we have an entire subject on prompt called as prompt engineering. You might have heard of it. Okay, prompt engineering, where they are completely educating the people on how to ask the right question to the system so that you will be able to get the right answer. So that our time and other resources will be conserved. If you are doing research, ChatGPT will be able to help you with a lot of content, but you have to ask the right question. Okay. Next is history of Gen AI. Why we talk about generative models so much, or why we say that AI is not our future, AI is our present. It is because of some of the milestone inventions. What has happened? In 1964, the first chatbot was developed by the MIT computer scientist Joseph Weizenbaum, and the name of that chatbot is Elisa. So this is a remarkable achievement in this generative AI model. And in 1999, NVIDIA came with the graphical processing unit, the first GPU. So the invention of GPU is also playing a major role in the development of AI. And in 2004, Google came up with this autocomplete option. That is, it is able to predict the next word. In the search engine, if you type something, Google was able to predict what will be your next search. Okay, so this was done in the year 2004. In 2013, one of the generative AI model, which I'll be explaining in class also, that is variational autoencoder, was invented. And in 2014, the generative adversarial network GAN, which is very popular. All of us may have come across this GAN generated images one or the other time in the near past. And so this models came up in 2014. And in 2017, another very great milestone is done. That is the transformers. The BERT model was developed, and these transformers are playing a very major role in all the language models what we see, LLMs, that is a large language models, or all the credit of text translations what we see today. Whenever we come across a content, if you press translate, it is able to translate in any language. In YouTube or Facebook or any kind of social media, you are able to change or translate the content to any language what you want. The credit goes to transformer, the invention of transformer. The text summarization, everything is possible. NLP, natural language processing, has been successful, or the dream of NLP is possible with the help of transformer. So that also I'll be explaining to you. And in 2018, OpenAI came up with a GPT. Uh, 2022. So thereon we are seeing an AI revolution, and we will see some of the applications. Applications of Gen AI, just I have cited only a few. So purely the application of generative model will lie on your creativity. Okay. So it is right now, it is used for image generation. With the help of a prompt, text prompt or image prompt, you will be able to create images, you will be able to create audio, you will be able to generate videos, you will be able to generate text, as well as you are able to translate text. Similarly, you are able to generate data, synthetic data. Even I have worked on synthetic data. When I want to prove scalability for the algorithm what I developed, I generated data artificially with the help of Veka tool in lakhs. I generated 1 lakh, 5 lakh, 10 lakh, 50 lakh. No, I generated such and such synthetic samples. But because that amount of sample was not existing on those days when I was completing my research in 2014. But to prove scalability, I generated vast amount of data. In the same way, today in different applications, there is no data available. But I know that is this is the characteristics of data, or I have one or few samples. So these samples can be used to generate more samples. So in that way, it is able to help a lot of research. And then it's also useful to generate codes. Okay. Gen AI is also helpful in generation of codes. So this I have already explained you. So generative AI, it is going to understand the relationships or the features of the data what you present, and it is going to after understanding and after characterization and discrimination of the properties, it is able to come up with generation of new data, new content. And if you see, I'll not be touching into the probability aspects today, but if you see this entire subject at the minute level, at the end level, it is all probability distributions. Okay. So if you are good at probability distribution, then you'll be able to master this particular subject. Yes. So these are some of the 4 models which we are going to discuss now in this session. Deep generative models. The first and foremost will be generative adversarial networks, GANs. So here, GAN, as you know, all know, it is going to create images, but they are not really existing. They are all fake images. So it can generate image or any other even multimedia content like audio or video based on the instructions what you give. The instructions may be an image instruction or it may be a textual instruction. It will be able to generate pictures for you. And transformer based models, so these are the basis for the ChatGPT or Copilot or other kind of AI based language models what we see. So their basis lies on this GPT, generative pre-trained transformer. So here they are making text translations as well as they are making content creation. So if you ask a question, it is giving you answers, no, very nicely structured answers. Today our students prefer to learn from ChatGPT rather than reading contents from books. Okay. Variational autoencoder. So this is also an important generative model. It is able to generate image as well as it is able to make anomaly detection. That is deviations. When the probability distributions is deviating, the autoencoder will be able to identify that. So any type of systems where you are making fraudulent detections or you are trying to predict the outliers, you will be able to use this model called variational autoencoder. And diffusion models, uh, these models are used to create images and videos, but this is a very stable model. And I'll say, no, I'll come across one model. You'll be very interested to know how this diffusion based models are used today. So these are the 4 models we'll be discussing: GANs, transformers, VAE, and diffusion models. First is GAN. Generative adversarial network. So GAN is invented by Ian Goodfellow in the University of Montreal. It is in Canada and in the year 2014. So they presented this idea in a paper titled Generative Adversarial Networks. So this GAN consists of 2 networks. One is 2 CNNs actually. CNN will be explained in the next session. So for those people who are very beginner, you can get an idea from the next session. For the others who are able to understand, so it is a 2 convolutional neural network, one called as a generator, the other called as a discriminator. So they work in against each other actually. So that is why the name adversarial is there on the name of the model, adversarial, because they work against each other. So we call that as a zero-sum game. That is, if one wins, the other fails. And if the other wins, the other network fails. That is, you're having 2 networks. If one is having an error on the prediction, it means the other network has succeeded. If the other network is having an error, it means the other has succeeded. It means generator and the discriminator. So what is the purpose of this generator and discriminator? So that's what is the main ideas. So it is used for image and video generation. So it's a very good model. It was a very promising model. So you're having 2 networks. One is the generator, the other is a discriminator. So generator, the purpose is, as the name suggests, it is going to generate new samples, that is fake samples. Okay. The neural network here, it is going to create fake input or fake samples from a random vector. So when it starts, it is going to start with the random vector. You can even call it as a random noise. Some values, it will create a fake sample. Now this fake sample will be given to the discriminator. Okay. So what is the purpose of the discriminator? The discriminator has to distinguish between whether this particular sample is a real sample or a fake sample. Okay. So if it correctly finds out that it is a fake sample, now the generator has generated it, and if the discriminator also finds that it is a fake, then who is winning? Discriminator is winning and the generator is failing. Okay. Now the generator has to update its model. because it has generated a sample which is easily identifiable or detectable by the discriminator. Now, these two neural networks work against each other. So the discriminator is trying to identify all the samples correctly, whether it is fake or real. And the generator is trying to generate samples which look like real or which could fool the discriminator. So this is the purpose of these two convolutional neural networks, one called as a generator network, the other called as a discriminator. So once these keeps on iterating till there is a point that the generator is able to create images which is not identifiable by the discriminator. So this is the architecture of the generative adversarial network. So you're having some random vector. So this is given as the input to the generator network. And now this is generating a fake sample. The discriminator, it gets both the real samples as well as the fake samples. So now both are given together. The discriminator will start predicting whether it is a real sample or a fake sample. It's a binary classification model. So it predicts either it is real or fake. So based on the result, if it is saying false positive or a false negative, then it needs to update itself. If it is truly guessing it, true positive or true negative, then in that case, the generated model will be updated. So these two models will be updated continuously. They'll be trained continuously till they reach their maximum performance. That is, since it's a GAN, and the purpose is to generate false images, which is not identifiable by human beings as fake images. So the generator will have to perform in its maximum. Okay. So the advantages of GAN is both these models are continuously improving. So we get very accurate results. And then this GAN model can be used for data augmentation. So in deep learning, you are having something called data augmentation. You may have very less amount of data in the real time, but deep learning is able to take any number of input, large number of samples as input. In this case, you can augment the data by in handwriting recognition. When if you have a handwriting 1, 2, 3, 4 and all written on a paper, a human will be able to predict a 2 even if the 2 is an inverse to 2. Okay. So suppose if the 2 is inverted, even then a human being will be able to say it's a 2, but the machine will fail. So this data augmentation, normally what it does is, it takes an input, it makes the rotate the inputs in different angles. Okay. It makes a lot of geometrical transformations and it will feed extra inputs to the training model so that the training model will be efficient. In the same way, GAN can be used to generate a lot of images. I'll see you some of the real applications also. I'll take you through some of the real applications also. And similarly, GAN can be used for pre-processing, that is to enhance the quality of the images, say in the case of satellite images or some medical images. If the quality of the image is not good, you can use GAN to improve the get an enhanced image. So it is used in image processing and biomedicine. It is also useful to predict, come up with high quality synthetic data. So this data can be used for research and analysis. When COVID came, there is no samples on COVID. So we were not able to conduct any research on to come up with drugs, to come up with vaccines. So we'll have to wait for some time till many people have been infected and many have lost their lives. But these kind of models could support with synthetic data. If you understand the characteristics or if you input the data correctly, it will be able to generate lot of data. Okay, so we'll see some of the tools which are based on GAN. So GAN is a generative AI model, and I'm giving the name of some of the tools which is implemented based on GAN. So deep fake, so it's very famous. It is able to generate synthetic images and video based on some, if you give some individuals, now it will change the features and it will create new samples. So that is called deep fake. Okay, and then style GAN. This is also used to artificially generate images. But the only thing is, in the image, you will be able to change the styles, shape, pose. You'll be able to make some modifications in the generated image. So that is style GAN. And the next one is cycle GAN. So this is very useful in medical imaging. So this cycle GAN, it is used to convert the MRI images into CT images. That is, if you see CT image, takes a lot of radiation. So the patient who is taking a CT, he will take lot of harmful images inside. But MRI, comparatively, it is not harmful. Okay. But for a study, suppose the doctor needs both the MRI image as well as the CT image. Okay. And you have only the patient's MRI image of a brain. From MRI image, you will be able to generate the CT image. So this is one particular tool called a cycle GAN, which is helping to generate MRI images, sorry, CT images from MRI images. So in this way, today we are using this generative model in different applications in research, medicine, and other areas. Of course, entertainment also. So the next model is transformer. So the transformer based model, it was originally published in a paper published by Google in the year 2017. So it is like Google came up with this in 17, and in 18, OpenAI came up with GPT and so on. No? They both work in parallel. So this transformer solves many of the problems in the domain of natural language processing. They try to predict, initially, their ultimate aim was to predict what is the next word in a sentence. Okay, when you are writing email, you are getting prompt about the suggestions about what is the next word. When you are searching for a keyword in a search engine, Google is saying what is the next keyword. So only for this type of sequential processing, it was used initially. But now transformers are used for content generation. It is used for translation because of the power of transformer. Initially, in this paper, the actually before transformer, the RNN network, the recurrent neural network, which is coming from machine learning, and then you study that in deep learning. So this RNN is the base for language modeling. So RNN is used, but they don't have this memory. They cannot remember the previous sentence, the previous sentence. But when you're speaking, so even if you see my conversation, my every sentence what I'm speaking depend upon all the past what I've spoken. And every next sentence what I'm going to speak, it depends upon what I'm speaking now. The context is very important. The context is understandable only when you have memory. Though now you have not written any notes, if you are listening to my class in the front, you are unable to understand the context in which I am speaking because you are correlating every sentence with the other and so on. Okay. So if the same thing is possible, then we call such a generative model as transformer. Okay. So how it is going to do it? It is going to do with the help of two major aspects. One is self-attention. Okay. So this self-attention is the important innovation of this paper, Google's paper. The title of the paper is Attention is All You Need. Okay. Self-attention and positional encodings are the two important aspects of transformer, which is a greater innovation when compared to all the existing language models what was there until 2017. Okay. So we'll see what is self-attention. Now, every word, it just till this transformer modeling, self-attention and all, people were thinking that when the words occur together, they are related. But there is always a chance that the word which is occurring even a distance, no, over a long distance, though they have some relation. Okay, that is the connectivity. So that is an important point. So this algorithms try to focus on how every word is related to each other, even when they are at a distance or they are closer. Okay. A transformer is made up of lot of layers, and these layers here we call it as transformer blocks. And these layers are self-attention layer, you are having a feed forward layer and a normalization layer. So people who are beginners, any neural network, you call it as a feed forward network. Okay, it is going to give the input in the forward direction. So you call that as a feed forward network, and the error is always back propagated. So this process you call it as back propagation. Okay, so these are all some of the layers what is available in the transformer and the process. The first and foremost is in any information retrieval technique or document clustering technique, you do something called tokenization. That is finding the root word, breaking the given input sentence into words, okay, or tokens. Now, after you take tokens, like images is having features. An image has an edge, the image has a color contrast, an image has a hue, saturation, and all. A word also has certain features. What are all the features, no? What are the features? A word has a gender. When I say she, it means a girl. When I say he, it means a male. A word has a gender. A word has a plurality. That is, it may be a singular form, it may be a plural form. A word has a tense. If I don't follow the tense, if I don't follow the grammar, my language will not be understandable to you. So every word has a meaning by all these things. Okay, this you call it as the meaning of the word, not just the word. To understand the meaning, you need to have all these features. What are the features? What is the gender? What is the domain in which the word is coming from? What is the plurality? What is the tense, etc., etc.? All these features, if you form as a numerical vector, you call that as a embedding or word embedding. So it's a numerical vector. If the words are having closer meaning, then this numerical vectors will be closer, will be similar. If the words are too different, they are entirely different in context and all, these numerical vector value will be too different. Okay, they'll be dissimilar. Okay, so word embedding is one thing, and then positional encoding. The other very important innovation of transformer is for every token, it is going to give a number according to the position. In a sentence, when it is spoken, every word is given a position number. And these two, word embeddings and positional encoding, they are merged together as a single vector and it is given to the network. Now, the network has different layers, and the first and foremost is the attention layer. Okay. In the attention layer, the main purpose is to understand the context. Attention layer or the purpose on it is to understand the context. What do you mean by context? Say, we have two words in computer science, Java, which is a coffee, and Java is a programming language. I enjoyed Java. Okay, I say. Now, this enjoyed Java, it can mean I enjoyed the coffee or I enjoyed learning Java or learning the programming language or doing the programming language. But when I add the next sentences, okay, we had Java when we were all there in an out stay, when I'm party with my friends on some place and all, or I happen to drink this Java when I was somewhere. So when you see more and more words, the context differs. It is no more programming language. It is talking about the coffee. Or if I say I enjoyed Java when I was in my college, I enjoyed programming in Java. When I add more words, now the context comes in. So self-attention, it assigns some weight to each part of the input. Okay. So this weight will signify a particular input. Ipo Java when the coffee solra, but that's very important. The word coffee is very important. The word code is very important to differentiate whether it's a coffee or a programming language. So depending on these words, the weight will differ. Okay, and some words will have less weightage, and some words which are very crucial in understanding the context will be given a higher weight. So this type of establishing a context, you call it as a self-attention layer. And this is the architecture of transformer model. So you have a positional encode, you have an input, the input is tokenized, and the words are having some features like gender, plurality, the tense, etc. And then you have a number over the position. These two put together, it is given to the other layers, that is the self-attention layer and the feed-forward layer. And finally, you have an activation function. So these are also, you may be familiar with neural network. So softmax is one of the activation function, which will be a probability based activation function. So it will take any input and it will give us output a value in the range of 0 to 1. It is a probabilistic activation function and you will be having the output. So this softmax function is used to predict uh, the probability of which word is the maximum possible word there. Okay, suppose if it is used in a next word prediction, now the softmax will help to predict what will be the apt word coming there. If it is a translation again, the softmax will help you a lot. Earlier, now I was doing this translation for IIT NPTEL courses. Uh, Earlier, when I was using it in 2019 for the first time, Google was not translating it very nicely. It will translate every word by word without understanding the context. So it will give very rubbish meanings. But now, if you see translations, it is better because Google understands the context. Okay. Yeah. Advantages. So when compared to RNN, before transformer, we were having RNN, which could process these natural language. But the thing is, RNN is not possible to make it parallel, but transformers are running in a parallel manner so that it is scalable. Okay, and it's also versatile in the sense the transformer can be applied for different purpose, language translation or text summarization generation and so on. And the training time is also comparatively lesser when compared to RNN or LSTM. So the transformer based models is OpenAI's ChatGPT or Microsoft's Copilot. Even you can use Copilot. Copilot will generate beautiful codes also. And Google's Bard and the Alpha Code, it is completely meant for code generation. So these are all some of the transformer based tools what is there. Next is diffusion models. So it is developed in 2015. It is otherwise called as denoising diffusion probabilistic models. So this is ultimately creating images or sounds by understanding the data what is there. So how it does is, actually I'll be explaining to you in a simple process. It is having a two-step process. So we call something called diffusion. In physics, you might have learned a concept called diffusion when something moves from one higher medium to lower medium or lower medium to higher medium. So here what you're going to do is, if you understand the architecture, yes. So you are having a data, the forward diffusion, what it does now, and this noise, it tries to remove every noise and add the detail what it has missed in all these stages, and it is able to get back the original in some to an extent. Okay, so this forward process of adding noise to the original image, you call it as forward diffusion, and the reverse process of reconstructing the distorted data or reconstructing the original data, you call it as reverse diffusion. So this is learned through the process. The original image to chaotic version, there the tracing is done and it tries to understand the data what is there, and because of which it is able to do it. And diffusion model is one of the stable model. If you see GAN and diffusion, they are used to generate images or any multimedia content, audio, video and all. But the thing is, diffusion model is very stable. The biggest advantage of diffusion is its stability, and but it takes a long time to train. Why I call GAN as unstable is because it is an adversarial network. There is a lot of problem arising if the discriminator is fooled in the first step itself. Adversary, a generator is generating something and the discriminator is fooled means the generator will be start generating only similar kind of pixels. Okay, similar kind of images. Ma'am, should I stop? Coordinators,
Ma'am, yes, ma'am.
should I stop, ma'am?
Yeah, yes, ma'am. Whether your session is over, ma'am?
Yes,
Whether
yes. I'll wind up. I'll wind up.
yeah, okay, ma'am. Thank you, ma'am.
Okay.
Thank you, ma'am.
Thank you.
Thank you for your session, ma'am.
Yes. In diffusion model, we have a very high quality. And I'll just introduce about the two tools. One is DALI model. The other is the stable diffusion model. இந்த ஸ்டேபிள் டிஃப்யூஷன் மாடல் தான் இன்னைக்கு எல்லாருமே நம்ம தமிழியன்ஸா இருக்கிறோம்னா கோட் மூவில நம்ம யூஸ் பண்ணிருக்கிற எல்லா டெக்னிக்ஸுமே வந்து the de-aging techniques what is used, all the AI animations what is done, it is done with the help of stable diffusion. So ask Copilot is giving the same information. Okay, what I would like to VI is, yes. So one thing, all these models, generative models, what I'm talking, they all rely on foundational model. That is the models which are trained on terabytes of data. Okay, but these foundational models you and I cannot create because we don't have that GPUs, that terabytes of data. We don't have access to all these things. We don't have access to all this hardware capacity. But these generative models are already trained, they are pre-trained, and these models you call it as foundational model. And what you can do is you can change this foundation model or tailor or tune this foundation models according to the specific application what you want. Okay, and you can improve the accuracy of that by improving the data what you give to the systems. Okay, I'll conclude. Yes, darker side, there is no privacy concerns, there is no intellectual property concerns because we are going to access the data what is available in internet. Okay, we are not concerned about copyrights and all. That is an issue even when you are using chat gpt for research purpose. We are like having a question of IP. Okay, and deep fakes and other kind of AI generated content which looks like real, it's a huge threat for security, national security and privacy. So to summarize, I have just discussed about the GAN, transformer and diffusion models. And every time we were saying that AI is our future and all, so we should start thinking about considering AI as our present. And now we are all teacher probably, and this profession here we are creating. Okay, so I just felt that this quote is very important, that we are also in a process of creating other professions. Thank you all for this wonderful opportunity. I thank the organizers for giving me this opportunity to present a session, and looking forward to have any discussion, or we'll move on to the next session.
Any queries, please? Any questions? Okay, let's wind up the session. Thank you so much, Dr. Jesu Vedanahi ma'am, for such an engaging and enlightening session on generative models. Your detailed explanations and in-depth knowledge have provided us with valuable insights into this fascinating and complex area of deep learning. We deeply
Thank you, sir.
appreciate, yes, ma'am. We deeply appreciate the time and effort you have taken to guide us through the key concepts. And I am sure everyone here has gained a deeper understanding of generative models and their potential applications. Thank you so much. Thank you so much, ma'am.
Thank you. Thank you so much for inviting me, and I wish you good luck for all the participants and the organizers. Thank you. Thank you.
Thanks a lot, ma'am. Thank you. Thank you.
Participants, kindly wait for another 2 more minutes to start our second session. Kindly wait. Cynthia ma'am, good afternoon ma'am.
Good afternoon, ma'am.
Can we start our session? Yeah, yes ma'am, you are audible ma'am. Can we start our session
Yes.
ma'am?
Yes, ma'am.
Yeah, thank you ma'am, thank you. John sir?
Yes. It's my privilege to introduce the research person for our second session on deep neural networks, Dr. D. Cynthia Vinodini. Dr. Vinodini currently serves as the Associate Research Lead at Truviti HR Solutions Private Limited, where she has been at the forefront of research and development in artificial intelligence and deep learning. With her extensive experience in this rapidly evolving field, Dr. Vinodini has been instrumental in driving innovation and applying deep neural networks to solve real-world challenges. Her expertise and insights are sure to deepen our understanding of how these networks function and their growing impact across various industries. We are honored to have her with us today to share her knowledge and insights. Please join me in welcoming Dr. Cynthia Vinodini to lead the session. Over to you, ma'am.
Thank you, sir. Yes, I'm privileged to. Yes, can I start, ma'am?
Yes, ma'am.
Yes ma'am. Yes ma'am, yes ma'am.
Good evening, everyone. Today I'll be speaking about the deep neural networks, and so these are the contents which I prepared for today's session. So I'll go very basic into what is neural network, its structures, and simple computations, and I'll complete my session with a small demo. And about deep neural networks, a small historic context. So it is inspired from our human brain. So our human brain is interconnection of many neurons. That's how we see, we do our activities. So based on these interconnections, our scientists have inspired, and they have built a model. And first model was started in 1943 by Warren McCulloch and Walter Pitts. And this McCulloch-Pitts neuron is a simplified model of our human neuron. Because it's simplified, it comes with its own limitations. And after that, 1958, Frank Wilson built a perceptron network. So this was used in simple pattern recognition tasks. Yet there was some limitation in handling non-linear problems, and because of this, this was in gaining popularity since 1980s. So after 1980s, they started developing multi-layer networks and the back propagation algorithm, which started the booming of this deep neural network. And our neural network, as I told earlier, it's a biological inspiration. So our human neuron is a composition of connection of multiple neurons, and this is a simple structure of it. It has many dendrites. These dendrites are connected to another neurons through synapses, and they connect using this, and it is processed, and finally the output is given at the output nodes. And same way, we have our artificial neural network here. This is a small neuron. Okay, and this is called as a node, and each node is getting input from different neurons at different levels, and that is actually computed here at Z. So we have multiple inputs to a particular neuron, and each is weighted using the weight parameters, and there's a bias parameter, and this is given a neuron node. And here it is a linear function, which is nothing but summation, weighted summation of all the neurons here. And finally, we'll have an activation function. We'll see about all this, and we'll have the output of the neuron. So what is the power of neural network is it learns from examples. It generalizes the patterns in the data. So usually in traditional algorithms, we program how it should learn, how we give the rules, like how we craft the features, how to classify, how to do particular functions. But here it will generalize the patterns, it will learn itself. It will develop its own rules, so making it more flexible for real-time applications like pattern recognition, classification, and predictions. So this is overall structure of a neural network, and there are many components inside the neural network. So three main primary components is this nodes, otherwise it is called as neurons. So neurons, as we have seen earlier, it is the basic block of a neural network. It is very similar to a biological neuron. So each neuron will get input from the previous neurons, previous layers, and this input will be processed within the node. And based on the activation functions, it will produce some output. So the neuron is organized into input layers, hidden layers, and output layer. So I'll go here. So this is a simple deep neural network structure where it has input layer, hidden. Here it has hidden layer as 3. We can have any number of hidden layers. And finally, there's a output layer. Input layer is something which get input, raw input from the domain. So there's no computation in this particular layer. So the information is passed to the hidden layer. In the hidden layer, this is where the actual computation takes place. So all kind of computations, all different features are extracted here, high-level features, low-level features, everything is extracted in this hidden layer. So after this hidden layer, we finally have the output layer. So in the output layer, all the processing will be taken place, and finally the output layer will be giving the output based on our application, based on how we need our output to be, and based on that we'll have response from the output layer. So hidden layer, I told you there can be multiple hidden layers, and based on how many hidden layers we have, it is called as deep network. So the depth of the network increases as the number of hidden layer is increased. So here we have some more components called as weights, biases. So what is weight is, I told you that two neurons will be interconnected. There will be connection between neurons, and each connection is given some weight. And this weight parameter is learnable. So while training a neural network, what will be changed is this weight. This weight that is associated with between the neurons is modified to get the required output which we need. So this happens in the training phase. And then biases. So bias will be given to each neuron. So this is an extra input. Sometimes this will not be given. This is to shift the output of the neuron to escape from some points. Like if we do not want a negative value in the output, we use this bias to shift the output of the neurons. So we'll have a better fit of the data. So yes, to minimize the error, we usually predict the error at the output, and that will be back propagated to learn the weight. So that will be seen later. So this is a simple computation. So this is one node, single neural node. So this will be getting input from n number of inputs. So here it is a simple 3 input node. So we have 3 input, and each input is given a weight. So so we'll have a small computation here, which is nothing but a weighted summation. So we see here summation of weighted inputs, and then we add a bias to it. So this is the input, weighted input which the neuron receives. So, and then this will be given to a activation function. So based on this activation function, we'll have a output. So what is an activation function? Activation function is something that introduces non-linearity into the model. So there are many activation functions which is used currently. Some activation functions are linear functions, which is we can see here there's a linear activation function and ReLU, which is rectified linear unit. So linear is nothing but whatever input we have, if the input is positive, all the negative inputs will be clipped off. If the input is positive, that is the weighted sum of all inputs, if it is positive, so the output will have the same output. When it comes to ReLU, it is rectified. That is, for all negative inputs, we'll be having 0, and for all positive, we'll have the exact replica of the input here. And this can be extended. So parametric ReLU is something in the negative side, we'll have an attenuated output of the input. And leaky ReLU is, again, we can shift the ReLU units. And these are some linear inputs, and we have non-linear activation functions. So non-linear activation is the most commonly used is sigmoid. So here we can see the sigmoid. So if the input is 0, we can have 0.5, and for all positive inputs greater than 0, the output will be limited from 0.5 to 1. Otherwise, if it is in the negative side, the output will be limited from 0 to 0.5. So same way, we have different activation functions. So activation function, now you can get an idea, which is nothing but for a non-linear activation function, it is a limiting function. You can see all linear activation functions, mostly it replicates the input to the output, but non-linear functions which we generally use is, there are other non-linear functions which doesn't limit, but mostly we use limiting activation functions, which is tanh, sigmoid. So this is some S type of curve where it limits the inputs which we receive to within a particular range. So generally what we use is sigmoid and tanh. So how to choose this activation function? First we need to determine what kind of problem we are going to solve. So based on the problem, that is based on our application, we need to select an activation function which can solve which will be important to solve. So as a thumb rule, we always use ReLU activation function. Only if the ReLU doesn't provide the required result for us, we go for other activation functions. And ReLU is usually used in hidden layers. And activation functions like this, limiting activation functions, the sigmoid, logistic, and tanh functions, which will not be used in hidden layers, but they will be mostly used in the output layers. So in the output layers, we go for this limiting function, sigmoid, tanh, and logistics. And we use another function called as the switch function, which is used when we have depth greater than 40 layers. That is, the hidden layer, number of hidden layers is usually above 40. And finally, now based on our applications, if it is a regression type of application, we generally go for linear activation function. So if it is a binary classification, it is sigmoid or logistic functions. So if it is a multi-class or multi-label classifications, we go for softmax or sigmoid activation functions. And again, based on the hidden layers, what type of architecture we use. If we are using CNN for hidden layers, we go usually for ReLU. And for recurrent neural networks, we go for tanh or sigmoid activation function. So next is training the network. So during training, we'll have a set of set of inputs, and to that particular data, we'll have a set of output labels, that we know what is the output, required output. So we have input and output now. So now this will be given to our network architecture. So once this is supplied to the network architecture, the network, when an input is supplied to the network architecture, it will do all the computations which we discuss now. So then it will result in a particular output. But now we have a desired output, which is required now. So now there's a desired output and the output generated by the network. So now the network will calculate the error. So the predicted minus the actual output will give us some error, and based on a loss function, we will back propagate this error back to the network. So once this is back propagated, now here based on the we can use many optimizers like gradient descent, and this is used to reduce the error. So the weights and bias are adjusted so that it minimizes the error which we have calculated. So once this is done at multiple times. This is called as epoch, and in each epoch, multiple times of calculation is done. Multiple time of calculation is done to reduce the error. So usually we have 1,000 epochs and sometimes even greater than that to converge to the required output. So once this is done, the weights will be trained using this back propagation algorithm. So once the weights are trained, now this trained network weights along with the architecture can be used for testing purpose and validate the networks. So now I have took a small simple network called the Alex network, which is a computer vision application. So we'll see how this network works, how the computation is done here. So this is the basic architecture of a AlexNet. So this AlexNet has a size of 224 cross 224 cross 3. So the image size here, which we need to supply to this AlexNet, is 224 cross 224 cross 3. So 3 is the number of channels. That is, usually we have color images, which is RGB. So that is 3 here. So to this image which we supply here, we use the first filter we use is size 11 cross 11 and with a stride of 4. Now this in this AlexNet, they have used convolution network. This is a convolution layer. They have used pooling, max pooling layers. We'll just see what is all this convolution layer and max pooling layer. Then we'll come back to this AlexNet. So we have convolution layer here. So what is convolution? Convolution is generally adding weight, just summing all the inputs, weighted inputs. So if we have a, you can just see here, this is an input matrix or image like we can take, and this is given to a filter. So convolution of this image and this filter. So this is a 3 cross 3 filter. When we keep it on top of this 3 cross 3, this is all 1, this is all -1. So this is called as basic. Sir? Yes, sir?
डीप लर्निंगचं घेत होती ती बघून मी म्हटलं काय आवाज नाही रे म्हणते
Can you please come in English?
फीडबॅक फॉर्म टाकलाय मी तर ते टेस्टिंगचं काम घ्यायचं होतं बोलून
Okay. So can I continue, sir? Okay, this is an input image. So to which we give a filter here. So the filter is of size 3 cross 3 and the value within the filter is called as weight. This is called as weight. So we will place this filter on top of this input image. So what happens? This should each element-wise element multiplication. So 7 into 1 plus 2 into 0 plus 3 into -1 plus 4 into 1 plus 5 into 0 plus 3 into -1, and same way the lower row. So when we do this, what happens? All this will have the same value. When this is multiplied by 0, this column will become 0 and this column will become -3. So 7 plus 4 plus 3 will be 14. And here 3 plus 3 plus 2 will be 8. So that is -8. 14 minus 8 will be 6. So 6 will be the first value here. Now we'll go after computing this portion, we need to stride it. So from 3, 2, 3, 3, 5, 3, 8, 3, 2, 8. On top of this, we'll have the filter placed, and this will, we need to do the same math here. So once that is done, the result will be -9. So this way we have to make next, right? So now this portion of 3 cross 3 from the input will be selected, and we can do convolution with the filter and we'll have a result here. So this is how we have an input and we have a filter. We convolve the input and the filter, we'll have a final result here. This is for a single convolution filter. But when it comes to deep learning, it will not be just one single filter. We'll have multiple filters. See here, we have a filter of dimension 4 cross 4. That is 4 rows, 4 columns. And we have 3 channels. That is 3 different. We have 3 different filters. So this is one set of filter. This is called as filter 1. Then we have second set of filter. So each filter can have different weighing parameters. So green color shows a different set of weights associated with the filter, and same way blue has different set of weights associated with it, similarly brown. And same way we have a filter 2, which will have different set of filters, weights associated with it. And here, this is an example. It shows of size 4 cross 4 cross 3. Sorry. Okay. So now we have an input image here. This should convolve with this filter. So what happens? Just place this filter on top of this input image. So this is a 4 cross 4. So first 4 cross 4 size will be taken, and the same math will be computed. So this will result in one value. So this in the input image, it is 4 cross 4 cross 3 because it has 3 bands which will be convolved with this filter, and finally we will have one value for 4 cross 4 cross 3. So that will be the first value in this output 3 cross 3. So why the output is 3 cross 3 is because, so now we have 4 cross 4. Now we will stride to it. So what happens again next, this 4 cross 4 will be selected, and then after that this third 4 cross 4 will be selected. So totally we will have only 3 cross 3 values as the output. So the image size is 6. For a filter of 4, we will have only 3. So to uh, to make it more generalized, the total size minus the filter size plus 1 will give us the output. That is 6 plus 4 minus 1, which is equal to 3 will be our output here. Same way for filter 2, we will have another 3 cross 3. So here we just have 2 filters. So these 2 values will be concatenated one after the other. So this will be the feature extracted using this convolution layer. I think this is clear. Should I repeat? Is this clear? Okay. And now this will be next given to a activation function. So this activation function, based on the value it has here, will be giving a particular output. So what will be the output? Will again be this 3 cross 3 cross 2. So this is for basic computation involved in a convolution layer. Next, we will go for strided convolution. So what is a strided convolution? You see here, for a 3 cross 3 filter window, see this blue is creating one value. So stride one is just we are striding with 1 pixel length. So the next we'll have a red shade, and then again we are striding to 1 pixel length. So we'll have a green here.